Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Welcome to Lesson 21, Comparing Linear and Exponential Models again. All right, again and again and again, the classwork opening exercise. General form of a linear model. Now remember, linear equations are y equals mx plus b in the slope-intercept form, where m is slope and b is the y-intercept. But we're doing a general form, which is function notation, f of x equals. And instead of using m, we're going to use the letter a, x plus b. Meaning of parameters a and b. So they're going to ask us to use a and b here. So that's why I used a instead of m. Okay, so y equals mx plus b, f of x equals ax plus b, means the same thing. M and a are equal, f of x is equal to y, and the b's, of course, are the same. An exponential model, in other words, would also be an f of x equals function. And exponential model has a number out in front, we'll get to in a moment, a b, in parentheses, and then an exponential variable. Okay, so now it says the meaning of the parameters of a and b. Okay, so a is the slope of the line, or you could call it the constant rate of change, and b is the y-intercept, or we could say that's the f of x value at x equals 0. So 0, comma, f of x. Okay, exponential model. A is the y-intercept of the f of x value when x equals 0. And b is the base, or we can call that the constant quotient of change. Okay, so example. Well, let's just choose an a and a b. That's all they're asking us to do here. So let's make a 2 and b 3. So f of x equals 2x plus 3. Okay, now doing the exponential function, f of x equals. Okay, so a was 2 here, but a is our slope or constant rate of change, and b is the y-intercept. Over here, a is the y-intercept. A is the y-intercept, so I am going to stick with y-intercepts going in the same location. So our b was 3, our y-intercept was 3, so I want the y-intercept to be the same for this function because we're comparing them. So I'm going to make a 3 in this case, not 2, and I'm going to make b, our rate of change, going to be stay with 2. Okay, so it's kind of a switcheroo here. Rate of change, y-intercept, y-intercept, rate of change. Why do we say ax plus b, and why don't we say ba to the x? Well, whenever we do general forms of equations, we just go in alphabetical order, and that's just the way it works. So a does not equal a in this case. A equals b, and b equals a. So, rule for finding f of x plus 1 from f of x. Starting at the point 0, 3, our y-intercept, to find f of x plus 1, we're going to add 2 to f of x. And this f of x plus 1, by the way, just simply means the next x value. So if x was 0 originally, then the next function value would be 0 plus 1, or 1. The next one would be 0 plus, or 1 plus 1, which is 2. The next one would be 2 plus 1, which is 3. So what that means is we're just adding 1 to the prior x value to get to the next value. And our rate of change is how much that's going to change each time we change the 1, because 1 times 2 is 2, and then if this x is 1, 1 plus 1 is 2, but 2 times 2 is 4, and so on and so on and so on. In the exponential model, we would again start at the point 0, 3, our y-intercept, And to find f of x plus 1, we're going to multiply f of x by 2. Over here we added 2. Here we're going to multiply by 2. So let's create a table. All right, so let's switch to another color here. How about blue? Okay, so we're going to have an x value. And we're going to have an output function value of f of x. So if I start with the y-intercept like it says to do, it says right here, starting at the point 0, 3. So I put a 0 here and a 3 over here. Well, why is that 0, 3? Because if I plug in 0 here, 2 times 0 is 0, plus 3 is 3. To find f of x plus 1, you have to add 2 to f of x. So f of x plus 1, here's our x. F of x plus 1 is 0 plus 1, which is 1. That's just our next value. And to do that, we would add 2 to f of x. So 3 plus 2 is 5. So if I substitute this in, 2 times 1 is 2. 2 plus 3 does come out to be 5. Okay, so this is what the rule is doing. So to get the next one, you take this one, you plug it in for x. F of 1 plus 1 is, or f of 2. So that would be 2. Add 2 to f of x, 7. So checking, 2 times 2 is 4. 4 plus 3 is definitely 7. So this works. So to get to the next one, 2 plus 1 is 3. And add 2 to this, and we get 9. 3 times 2 is 6, plus 3 is 9. Now doing the same over here, if I have an x and if I have an f of x, then we're going to start at the point 0, 3 again. 0, 2 to the 0 is 1. Don't forget that. Anything to the first power, or 0 to the first power is 1. 3 times 1 is 3. To get to the next one, find f of x plus 1. Well, 0 plus 1 is 1. It says to multiply f of x by 2. 3 times 2 is 6. So if I substitute in a 1 here, 2 to the first power is 2. 2 times 3 is 6. Okay, so now to get to the next value, 1 plus 1 is 2. 6 times 2 is 12. And if I check this, plug 2 in here, 2 squared is 4. 4 times 3 is 12. And then 2 plus 1 is 3. And 2 times 12 is 24. And when I go up here, 2 to the third power, well, that's 2 times 2 times 2. 2 times 2 is 4, times 2 is 8. 8 times 3 is definitely 24. Okay, so then it says to graph them. Hopefully in the student version that you have, your hard copy of your module, hopefully they gave you graphs, but if not, just use a ruler and use the measuring markers on the ruler, the units of measurement, to make equal squares. And I'll bring in a graph. Okay, so here's what our linear model looks like. The point 0, 3, 1, 5, 2, 7, 3, 9. Okay, so to graph the exponential, notice what we had to do to graph this. This had to be scaled. Look at the y values. Over here we went by 2s, 2, 4, 6, 8, 10. Over here we're going 10, 20, 30 because it grows so much quicker. So we're starting at the point 0, 3, and then we jumped all the way to 1, 6, where this was only 1, 5. So that was only a difference of 1, but then look what happens. It goes from 2 to, at 2 it goes up to 12, and at this 2 it went to 7. So it's gaining momentum, or getting larger a lot faster. 3 ended up being 24, and 3 was only 9 here. So it's almost triple already. So now story problem example. Okay, this is just an example. There's infinitely many solutions, but let's just say Charles had $3 in his bank account and earned $2 per week as an allowance. So then he adds the $2 to his 3 every week and doesn't spend any money. And like most banks these days, gets close to 0 interest, so there's no pennies added to it. Okay, there were 3 goldfish in the tank, and the population doubled every month. So that would be an explanation of that. So population is exponential growth. Okay, page 2 brings us to an exercise. So pause the video See if you can do this on your own. Unpause and see how you did. Okay, for each table below, assume the function f is defined for all real numbers. Calculate delta f, and the triangle is a Greek letter, delta. Calculate delta f equals f of x minus 1 minus f of x in the last column in the table below and show your work. The symbol delta is the context meaning change in. So we're going to, so let me give you an example. The slope is y2 minus y1 over x2 minus x1. So we could also rewrite this as the change in y. Well, if y went from 5 to 3, it changed by 2. So y2 minus y1 would be the same as saying delta y, and x2 minus x1 is the same thing as saying delta x. Just to give you an idea, you're getting into higher maths now, and we use the triangle meaning the change in. So delta, it's just another shorthand. Instead of writing all of this, we can do it with just two symbols instead of all these. Okay, just a form of shorthand, if you will. All right, so change in. Let's get back to what we're doing now. Okay, so it says, what do you notice about delta f? Could the function be linear or exponential? Write a linear or exponential function formula that generates the same input-output pairs as given in the table. So we're given 1, negative 3, 2, 1, 3, 5, 4, 9, 5, 13. Okay, so if we take f of x plus 1 minus f of x, so what they're saying is take x, and then, well, let's see. Okay, so f of x plus 1 would just be the next term. F of x is negative 3, so I'm going to write minus negative 3 right here. This is our minus f of x. This is f of x, so this is minus f of x. Well, what's f of x plus 1? F of x plus 1 is the term following f of x, and that is 1. Okay, so hopefully that makes sense to you. So this would be 1. That's the next term. It's the next y value. So think of it as y2 minus y1, like I just showed you in slope. And 1 minus a negative 3 equals 4. Now when I do it again, f of x plus 1 on this line would be 5. The next y value, 5 minus my f of x, which is 1, equals 4. Next one, 9 minus my f of x here, which is 5, and that gives me a value of 4. And then the next f of x, I should say, f of x plus 1 is 13, and f of x is 9. So 13 minus 9 is, again, 4. So you should have what's called a constant rate of change. So it's constantly changing by 4. And what they're asking us to do is write a linear or exponential function formula that generates the same input-output pairs as given in the table. So now we have a function f of x equals, well, I know my rate of change is 4, so I'm going to put 4x here. And to find my y now, I'm just going to pick one of these x's, substitute it in, and see what I would have to add to that or subtract from it to get the number we have. So if I put a 3 in here, okay, I'm looking at this right here. If I substitute in 3, so if I said, well, what's f of 3? Well, f of 3 is 4 times 3 plus some number b. So f of 3, which is 5, let me just substitute that in now. F of 3 is 5. 5 equals 12 plus b. Okay, simple substitution. And then to get b by itself, I need to subtract 12 from both sides. And when I do that, I get negative 7. So my linear function for this model is f of x equals 4x minus 7. And you can check it. 5 times 4 is 20. 20 minus 7 is 13. 4 times 4 is 16. 16 minus 7 is 9. 2 times 4 is 8. 8 minus 7 is 1. 1 times 4 is 4. 4 minus 7 is negative 3. So there is our linear equation. Okay, our linear function. Next one. So del f, change in f, equals f of x plus 1, which is 6, minus f of x, which is 2, which gives me 4. Del f equals f of x plus 1, 18, minus my f of x, which is 6, which equals 12. 54 minus 18 is 36. 162 minus 54, well, 162 minus 52 would be 110, but we're subtracting 2 more, so that's 108. Okay, a little bit of mental math there. Okay, so as you can see, our rate of change is not the same as up here, 4, 4, 4, 4. That is a constant rate of change, and linear functions are constant. This is exponentially growing. It went from 4 to 12 to 36 to 108. So this is an exponential function, so I would say f of x equals, and remember what a is our y-intercept. So if a equals 2, so remember it's f of x equals a times b to the x, and a is our y-intercept. So our y-intercept in this case is f of 0. So when I plug in f of 0 right here, I get 2. So f of 0 equals ax plus b. So f of 0 equals 2. We already know that because it's 0, comma 2. So f of 0 equals 2. That's my a. So I'm going to put a 2 there. And now I just have to find out what my base is. And that's going to be to the power of x. Okay, so how do we do this? Well, you look for a common quotient. So you just take any of these two numbers and divide them. 36 divided by the prior one, 12. 36 divided by 12 is 3. 12 divided by 4 is 3. 108 divided by 36 is 3. So that is my common, my quotient, my common quotient. So that is going to be 3. Okay, page 3 brings us to problem number 2, where it says, Terrence looked down the second column of the table and noticed that 3 divided by 1 is 3, 9 divided by 3 is 3, 27 divided by 9 is 3, 81 divided by 27 is 3. So all those fractions are equal, so there is a common quotient. So R equals 3. That's our common quotient. Because of his observation, he claimed that the input-output pairs in this table could be modeled with an exponential function. Explain why Terrence is correct or incorrect. If he is correct, write a formula for the exponential function that generates the input-output pairs in the given table. If he is incorrect, determine and write a formula for the function that generates the input-output pairs given in the table. Okay, so first things first, remember that we have to have delta f. Change in f is f of x plus 1 minus f of x. Okay, so if I take 0, that's my first term. 0 plus 1 is 1. 1 minus 0 is 1. But then if I come down here, f of x is 1, but the next term is 4. Well, to get the next term, we're supposed to plug in 1. So 1 plus 1 is 2. 2 minus 1 is not giving us the right amount. So in other words, what I'm saying is this is a difference of 1. This is a difference of 3. This is a difference of 9. And this is a difference of 27. Okay, so our f of x plus 1 minus f of x has to be the same every time. We have to have the same change in f, and we don't have that here. So he is incorrect. So we would say Terrence is incorrect. This is because the distance between consecutive x values is not 1. In other words, it is not constant. It is increasing by multiples as well as the t of x. Okay. So just because we had a common quotient, do not assume automatically that it's exponential. Check your x values. They have to increase by 1 while these have a common ratio. Number 3, a river has an initial minnow population of 40,000 that is growing at 5% per year. Due to environmental conditions, the amount of algae that minnows use for food is decreasing, supporting 1,000 fewer minnows each year. Currently, there is enough algae to support 50,000 minnows. Is the minnow population increasing linearly or exponentially? Is the amount of algae decreasing as a linear or exponential rate? And in what year will the minnow population exceed the amount of algae available? Okay. Okay, so let's take a closer look at this. There's a little bit of work involved in this problem. So a minnow population, a river has an initial, where is my pen? Why won't my pen work? All right, so initial minnow population will give us the point 0, comma, 40,000. 0 being the year, now, year 0, population initially 40,000. That's our y-intercept. It's growing at a 5% rate per year. So first year, this is going to increase 5%. So if I go in my calculator, take 40,000 times 1.05, okay, that's 105%. Increasing 5%, in other words, would be 2,000 fish. 2,000 is 5% of 40,000, so now we're up to 42,000 fish. Okay, year 2, we just do that again, and then times 1.05 again, and I get 44,100. Year 2 is 44,100. Year 3 is going to be 46,305. Year 4 is going to be 48,620. And year 5 is going to be 51,051 fish. Okay. So that's year 1, 2, 3, 4, 5, and the population's increasing. This increased by a rate of 2,000. This increased by a rate of 2,100. Or that's how much it changed, I should say. This changed by 2,200. This one changed by 2,315. And this one changed by well, let's see, 51,051 minus 48,620 equals 2,431. So as you can see, this is changing by more every year, so that's exponential. So we're going to say that is an exponential growth with our rate of change being 1.05. our quotient, our rate of change is a quotient, not constant. And now let's look at the other. So due to environmental conditions, the amount of algae that minnows use for food decreases, supporting 1,000 fewer minnows each year. Currently, there is enough algae to support 50,000 minnows. So that's my year 0, and that will support 50,000 fish. Year 1, next year, it's going to decrease by 1,000, so that's 49,000. Do I still have enough to feed the fish? Yes, there's only 42,000 fish year 1. Year 2, I can only feed 48,000 fish because there's less algae. Year 2, we had 44,000 fish. There's enough to feed. Year 3, we're going to drop down to 47,000 fish. I'm sorry, drop down to an amount that feeds 47,000 fish. In year 3, we had 46,300 fish. There's still enough to feed them. Year 4, we're going to drop down to 46,000 fish that the algae is going to be able to feed. And right there is where we have a problem. So we have 48,000 fish year 4, but only enough algae to feed 46,000. So 2,620 fish who are happy and eating now are going to be unhappy, and they're going to go belly up because there's no food. And that'll be the end. Okay, so I'll stop right there. So now let's bring in an explanation here. Okay, so we would say the minnow population is increasing exponentially. The amount of algae is decreasing the food supply that can be used to support minnows linearly. Solution methods to find when the minnow population will exceed the amount of algae may vary. The way I did it was just plugging in values until I found. We could have graphed it. So we need to find the number of years n such that, and they gave us the equation here. So 40, this 40 is in thousands, just so they're not dealing with really huge numbers. So that's our initial population. 40, that's our y-intercept in our exponential function. 1.05 is our rate of change, that's our base, to the power of n, where n is the number of years. And that has to stay greater than 50,000 fish initially, minus number of years n, which is 1,000 fewer. Okay, we need to find the number of years. So, and that says why? Well, that's because we have to have enough, the number of fish. When the number of fish is greater than the number of algae to feed them, that's when we have this guy not having enough food. So for n equals 3, we got 46.3. So they just rounded to, they just used decimals. So that's right here, that's that 46,300 is greater than 47. Is false. So 46.3 is greater than 47 is false. So in other words, there's enough food to feed the fish. But for n equals 4, when n equals 4, we get 48.6 and 46. 48.6 is greater than 46. That is true. So therefore, sometime after the 3rd year, the minnow population will exceed the amount of algae available. Okay, page 4 brings us to problem number 4, and it says, using a calculator, Joanna made the following table and then made the following conjecture. 3x is always greater than 1.02 to the x. Is Joan correct? Explain. Okay. Remember, 3x is linear. Rate of change of 3. Y-intercept of 0. 1.02 to the x is an exponential function where a is 1, because there's nothing out in front. That'd be 1 times, that's our a, 1 times 1.02, which is our b, our base, to the power of x. That's exponential. What do we know now about exponential functions? They grow a lot faster than lines, than linears. So if I bring my calculator in here and I put clear, and I put y equals clear, clear, all right, and I put the function 1.02 to the power of x and graph it. Okay, so there it is. It's, oh, what did I do wrong? Nothing. It's starting to grow. Okay, it was flat. It looked like it was flat, 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 and then it started to go up. You can't really see what's going on here because it's growing so slow. It's only 2%. So at 5, so if I hit trace, we have the point 0.01, which we aren't graphing here. We have the point, well, if I go to my table and I plug in 1, then I get 1.02, like this says. And if I put 2 in for x, I get 1.0404. And 3, you see what's going on here? This matches. And 4, 1.0824. And let's guess, 1.1041 will be for 5. And sure enough, 1.1041. And then 6, and so on and so on and so on. And now if I go back to y equals and put that in y2, and now she has a function 3x, that's 3x plus 0, y-intercept of 0, slope of 3, or rate of change of 3. And then if I hit graph now, there's that line, very steep, much bigger than this, but is it always going to be? Well, let's take a look. I'm going to change my window. And I don't care about negative, so I'm just going to put -1 so I can still see the y-axis. And my x maximum, I'm going to start with 1,000. And my y minimum, just so I can see the y-axis, or x-axis, I'm going to put -1. And the y max, I'm also going to go up to 1,000. And let's just see what that looks like. So there's the exponential function. And there's the linear function, and look what's happening. The linear function's coming up at a constant rate, but the exponential all of a sudden just started skyrocketing, and we almost got there. So I'm going to change my window a little bit more. My y maximum, let's make it 1,100. And look at what happens. Okay, so they crossed. And where did they cross? Second, calculate 5 for intersect and hit enter 3 times, and it's going to give me the point 351 comma 1054. So if my x maximum only went to let's say 400, it would give us a better picture, just a little bit more than our x value where they intersected. So there's the exponential function growing, and then here's the linear function, and sure enough, the exponential crossed it right there, and it is now higher. So here's our explanation. It says the function 1.02 to the x is exponential, and the function 3x is linear. So the exponential will eventually exceed the linear. Alternatively, students could extend the table to larger values of x to show that the exponential function will eventually exceed the linear function. 1.02 to the 500 is 19,957, but 3 times 500 is only 1,500. And again, if we just use this table, so we see exactly where it intersected. And it was at the point 335.5, repeating, comma, this number. Now that I think is to the e, so I won't even say what that value is. It is 1006 probably, something like that. Okay, so there you have it. Page 5 brings us to the end of lesson 21. Review the lesson summary and go to your problem set.